Welcome back to this is now session 13 that we're on. Okay, we're going to be looking at ionic, polar, and covalent molecules. But first, I just want to talk through the issue of metallic bonding. Remember we spoke about bonds and how they form, etc., etc. Well, what we need to do is we need to just discuss over here. Okay, we need to discuss metallic, because it's something that I haven't actually covered. I'm sure you've done it by now in class as well. But you know, we've got atoms. Let's take copper. Copper. Okay, we all know copper wire, iron, the steel around us, aluminium, etc. We've got the metals. Well, what does it look like inside a metal? How is that bonded? It's basically what we call a metallic bond. Whoops, that was bad spelling. Okay, for those of you who are very good at English, whoops. A metallic bond. What happens in a metal? Well, we've got a whole row of these copper, okay? But, well, what happens to the electrons here now? We've spoken about ionic, where the electronegative one takes the electron. We've spoken about covalent, where they share. Oxygen, nitrogen, fluorine, those are all covalent, where the electronegativity is the same. What about a metal? Inside a metal, what we've got is we've got the nucleus. I'm just going to put it down as there. We've got all these guys all nicely lined up. Okay? Now, inside the electrons, where do all these, because there's quite a lot of electrons inside iron, inside chromium, manganese, etc. Where do they go? Essentially what happens is they hang around between, okay, like that. They are called delocalized electrons, right? They actually are in a cloud around. Essentially, and I just as a concept, it's once again come a full, so it's a pure sharing, isn't it? It's not covalent bonding, but it's the same concept. The electron, the proton, rather, the nucleus, doesn't really care about the electrons. They are shared out amongst everybody, right? They are delocalized, so they don't necessarily belong one to the other. So each one sits in its own orbit, obviously around, but they are, generally speaking, spread out amongst everybody. So it's in a cloud, okay? It's an electron cloud that's around it. In 3 dimensions, obviously, because we've got a thickness. So we've got electrons all over the place with our nuclei, which are nice and ordered around the perimeter, or around the piece of metal or whatever it is, right? I know that was soap, but yeah, it was around the in the metal. Okay, so you've got to remember it as a 3-dimensional thing. Now, by virtue of this fact here, right? Let's just for a moment imagine that this here is a piece of wire, right? You know that an electric current, right? A current is a flow of electrons, right? Correct? In fact, the amp is defined as charge passing a place over a certain period of time, isn't it? So the flow of electrons. So hang on, what have we got over here? We've got electrons coming from the battery. Haven't we? They're coming from the battery into this wire. Well, what about these other electrons that are in here? What happens? Well, essentially, if you think of a long tray filled with marbles, that's what the inside looks like of the electrons, isn't it? And if you put a marble in this side, what happens at the other end? One pops out. So that's the delocalized. Electron comes in, one pops out. So as these 3 come in this side, what happens at the other end? Well, quite straightforward. 3 electrons pop out like marbles, and they carry on the flow, right? That's what's happening in a metal. Now, you remember we spoke about ionic bonds, because we're talking about what does this look like, what does this look like, what does that look like when they bond together, how do they do it physically? Okay? Well, an ionic bond, what did we do? We always look at the change in electronegativity between the two elements, A and B. All right? We said that if the change in electronegativity is high, all right? Now, there's a few definitions over here. I'm going to use the one mostly that I found. If the change in electronegativity is greater than 1.7, then it's ionic. Okay? Please, some people use 2, some people use 1.9. It is what is in your textbook to use, okay, what you're told. But in principle, we're saying that these two come along. This one is much more electronegative than this one, so what does it do? B over here basically takes the electron for itself. That's positive and that's negative side. Remember, sodium and chlorine. Okay? The electron was left that side. Please, if you have, for example, Mg plus 2, you have 2 Cl minuses, don't you? Okay? Because MgCl2. What happens is, this 2 electrons are coming down this side. Right? Because there's 2. Because there's 2 B's over there, right? The electron is sent to that side. So in that molecule, let's just have a look at it just for completeness sake. We've got that, right? So this electron is here and this electron is here. All taken from there, right? Like that. So there it is, right? This one has taken it, this one has taken the other one. Therefore, we have now got an electron taken both sides. So we end up with positive and a negative side, distinct, because this electron never goes back to that guy or that girl. I'm always using guys for this, but it never goes back to A. Okay, it stays with B because it's a greedy element. It takes it away. Then we said, all right, then we had pure, remember, we had over here, we had pure covalent. All right, pure covalent bonds. What do they look like? Well, we said nitrogen, 1, 2, 3, oxygen, 1, 2, and let's say hydrogen, single bonds. The electronegativity is same with Cl, right? Cl2, diatomic, remember? What happens here? They are single bonds, double bonds, triple bonds. So what's happening there? The difference in electronegativity is 0. Right? But guys, what happens in between? Because not all of these are actually ionic or whatever. It depends on the difference in electronegativity. What happens if the electronegativity difference is in between? Well, generally speaking, they give you a cutoff of 0.9 here, and anything below that is covalent. Some textbooks give 0.3. All right? But let's just keep it with what you know. Just put in the 2 extremes that you're going to use. Okay? What happens in between? What happens if I get a delta electronegativity of, let's say, equal to 1.2? Okay, 1.5. What does it look like? Well, let's have a look at A and B molecule, shall we? Remember, this is 2 molecules. Now, if it's here in between, A and B have got to be different, haven't they? So we've got A and we've got molecule B. They are joined. Here we go. This is A and B, right? Now we look at the electronegativity of this one, and let us say this one is 3 and this one is 1.5. So we've got delta electronegativity equal to 1.5, this guy here. It is not ionic and it is not covalent. What is it? In between here, it is called polar covalent. Ionic bond, okay, remember here, ionic bond, let's put it in red, no sharing. Okay. Okay. Pure covalent, perfect sharing. Right? There we go. Perfect sharing. They're the same electronegativity. They share perfect. They share absolutely without favor, so to speak. So we've got A, and now they're the same. So we get perfect sharing like that. The electron is spending equal amounts of time on both sides. So there's no positive or negative side, is there? The electron's always there. If it's here, right, it's balanced out on that side. So there's no charge, okay, on there. But now in between, let's have a look at in between. Polar covalent, right? What it means is that if there's a difference that lies in between, it means if we've got A and we've got B, B is more electronegative, so the electron spins, but it does this. Okay? Round and around. Okay? So most of the time, this side is negative. Most of the time, that side is positive. It's the proton, right? This side has got the extra electron. So the electron spends more time on the most electronegative side because that's the one pulling it the strongest, isn't it? So this one over here tends to make this side not totally 100% negative. This little delta, this little symbol here, that means partially. Partially, okay? If any of you go on into higher maths, you'll come across that delta over there. But this here is partially. It's negative, but not always, okay? This is called polar, okay? It's got a negative and a positive pole. It is still sharing covalent, but it's polar. It means that it is got a charge. Therefore, if it's got a charge, okay, it is going to act accordingly. So if we've got molecule AB over here, all right, there it is, all right, this side is slightly negative and that is slightly positive, all right, what is going to happen? This side is negative, so it's going to attract other positives, isn't it? This side is going to repel positives, but it's going to attract other negatives. Let us just look at water, okay? Okay. Let us look at water because it's a very important one. The electronegativity, first of all, let's draw our water. Remember, it was HOH, wasn't it? Because over here we had unpaired electrons, right? Remember that, the Lewis diagram? There's the Cooper diagram, the single bonds between. One electron shared the Lewis diagram with its crosses for the hydrogen, remember? So now, let's look at the electronegativity. Now, how do we do this? What you do is you take one side and you say, right, electronegativity of oxygen, let's look it up. Oxygen is 3.5. Electronegativity of the hydrogen on this lobe here is 2.1. Okay? So therefore, delta electronegativity is 3.5 minus 2.1. Okay? 3.5 equals 1.4. Okay? Change in electronegativity is 1.4. Okay? This is greater than 0.9 and less than 1.7. Did I say to use? We just use 1.7. Okay? Which means that this is not, this would be ionic, this is covalent pure, this is polar covalent. It means, quite simply, that the electron spends most of its time over there. But if now and then it's over there, but most of the time it's up here. Similarly on that side, right? It looks like that. So this side over here is mainly negative. This side is mainly positive. So what does it look like? It actually looks something like that, right? Where we've got our oxygen and our two hydrogens, and it's a molecule shaped like that, okay? Don't worry, the shapes and things we go into next year. So we've got this system here. Now what happens next? Well, what happens next is, this is a polar covalent. It is sharing, but it has got a pole. Which means, now let's think. What happens now? If we put this we've got, so I'm going to draw my molecule over here, and this is going to be a positive, this is negative. Now we've got lots of these floating around. It's a bottle of water or a beaker of water, right? There's loads of these floating around. Okay. Now, if I introduce another one of these, okay, what happens over here? The positive goes to the negative side, doesn't it? Like that. There's another water molecule. H, H, O. H, H, O. These go over there. Now, what happens here is these guys bond together. That there is called a hydrogen bond. Okay? Very important in the future. But that's how individual molecules of water all connect together. They form a hydrogen bond. Because they are polar covalent, one side's negative, one's positive. Okay? Same as a north and a south, isn't it? The one's going to migrate to find the other side. Like this. Here we go. Right? There's a magnet. I don't know if you can see it. Maybe if I put it on there, it's a little more sort of... And what happens here? Look. It aligns itself and the two come together, right? So that's a polar covalent thing, kind of like it spun it around and then pulled it in, okay? Now, what happens then when we dissolve things like salt in water? NaCl solid, okay? Now, when we put it into water, we end up getting this. Na plus Cl minus plus water. These here are now aqueous. They are ions in the water. How does it work? Let's examine our atom, molecule rather. Remember, we've got oxygen, hydrogen, and a hydrogen. The hydrogen side was positive, right? This was negative. So the crystal of this stuff gets dropped into the water. This, here we go, here's a crystal of salt. All right? This little molecule over here comes along to the edge of the crystal, right? Okay, hang on, let's pretend this is our crystal here. Let's see what happens. This guy comes along, it's floating around. This crystal is lying in the water, isn't it? It comes along, right? And over here, remember, we've got a sodium and a Cl ion because the chlorine has taken away the electron. So what happens is this water over here, this positive side, says hello to the chlorine. Doesn't it? Because chlorine is negative, right? What does this oxygen do? The oxygen says, okay, hello to the sodium. So this here, when it comes near a sodium, remember the lattice structure? Okay, we had it in a cube form. Okay, it's all in a lattice structure. Lattice means like a network. Remember we had sodium, chlorine, chlorine, sodium, sodium, chlorine, etc., right? In 3 dimensions going down. I'm not going to take time drawing it. But we had all of these, not N, that's nitrogen. Trying to go quickly. We had the sodium and the chlorine all linked together like that, right? Then what did we have? This guy comes along, all right? This not bipolar, this polar covalent molecule, it is in fact called a dipole, all right? It's got a positive and a negative side. Di meaning two. Two poles, a plus and a minus side, right? What happens is the positive side comes to this chlorine atom, right? And says, hi, okay, do you want a date? Sure. This person then pulls off there. So if the force of attraction between this positive side and this negative over here, if this force of attraction here, okay, here's my water coming along. If the force of attraction here is strong enough, it pulls the sodium off or the chlorine off this side. So it dissolves. This is a force over here, right? In other words, if the force between this side and this side here are strong enough to pull the individual atoms out, right? Then we say that it goes into solution, it dissolves, okay? Dissolution, okay? It goes into its ionic form in the water, okay? That is what actually happens when something dissolves. These, as long as, if this force is not big enough, it's not going to dissolve. It's just going to lie there, all right? A block of zinc, okay, just lies there, okay? A block of, I don't know, magnesium sulfate or one of those. I don't know, we'll have a look now which is solubilities and so on when we get to it. But that will just lie there. It just doesn't dissolve. Maybe one or two dissolve. Silver chloride, okay, doesn't dissolve, okay? So what happens is, therefore, the force is not strong enough with that one, okay? So if the force is strong enough, then it is soluble, okay? If it's not strong enough, it's insoluble, right? All it is this force, okay? It's the force that is exerted by a polar on an ionic or another polar. The rules are basically, it's soluble is like, dissolves like, and vice versa for that, okay? We're going to talk about precipitation, and I'll touch on solubility a little bit more in the next session. But I hope you can see that that's what's really happening in here, okay? It's going in, it's dissolved, we get the free ions, we get into the water. Therefore, what does it look like? Well, this is what we've got, isn't it? We've got our oxygen side and our hydrogen side, right? Hydrogen side, smaller. This side we said was positive. This is negative. Small amount, that little delta is a small letter D in Greek. It means small amount of charge. So over here, okay, let's just see the red, this one pulls off the Cl minus, right there it is. And this oxygen over here, just change it to a green. This one pulls off the sodium. So the sodium, which is positive, sticks there, and the chlorine, which is negative, sticks to that side. And then this little atom here, okay, off he goes. Oh, hang on, we can have another chlorine stuck on there. So what is happening is it's basically carrying away, okay? It carries away the ions. Because the force that this sits there with, okay, on the outside is enough to pull one off. And bit by bit by bit by bit, it chips it off, right? Okay. You will notice, as we will do in grade 12, right? Just as an aside, think about it. If you put a big block of salt, a solid chunk, okay, in there, it takes longer, doesn't it? Because more of these have got to chip away. Therefore, the finer the salt you put in, the quicker it dissolves. If you do that with sugar, you'll see very, very fine sugar, icing sugar, dissolves quickly. The big sugar cubes take longer to dissolve. Okay? That's because of that force, right? And remember, if the force isn't strong enough, then it will not dissolve. It's insoluble. Soluble insoluble. There's a set of solubility rules, okay, which are available. Those, once again, it's like the ions. You have to know those. It's important to know what's soluble and what's not. But what you will see is you'll see that generally speaking, they keep coming up with the same ones, okay? No, they're generally not going to ask you about cobalt chlorides, right? But they'll ask you lithium, sodium, potassium, magnesium, calcium, possibly, yeah, those ones, copper sulfates, okay? Things that are supposed to be general chemical knowledge, okay? We're going to move on from here now, okay? We're going to move now and we're going to look at, we're now going to start looking at different kind of reactions, okay? Yeah, and I'm going to be talking about endo and exothermic a little bit, and then we're going to look at precipitation, okay? We're going to look at ionic reactions, the precipitation, acids, bases, gas-producing reactions, okay? And once again, there's a few things there that are standard forms that you've just got to know. Okay. I'll be back with you when you're ready to get stuck into the next session. Thanks for listening. See you later.